Antiderivative examples number 1. So in our first example, we have the function f of x is equal to x minus 3. Now to find the antiderivative, we have to recognize that there is an invisible 1 in the exponent of the x variable that's usually is unwritten. So to find the antiderivative, we'll call it big F of x. We can use a formula that exists where for the variable x, the antiderivative is x to the power plus 1 divided by n plus 1 minus, here we have an x to the 0, which is unwritten, so there we have 3x to the n plus 1 divided by n plus 1 plus c. Thus, f of x, big F of x, is x to the here n is 1, so x squared divided by n is 1, 1 plus 1 is 2, minus 3 times x to the 0 plus 1 divided by 1 plus c. This can be more easily written as big F of x is equal to 1/2 x squared minus 3x plus c. We need our constant here, which can be an infinite number of possible constants that are removed through differentiation. So to check, we can write our f of x, big F of x, as 1/2 x squared minus 3x plus c. Deriving big F of x gives us f of x. So f of x is equal to 2 times 1/2 is simply 1, and 2 minus 1 is 1, minus derivative of 3x is simply 3, plus the derivative of a constant is 0. F of x is equal to x minus 3. We are consistent with the original function, so this antiderivative is valid. Example 2. F of x equals 1/2 plus 3/4 x squared minus 4/5 x cubed. Our antiderivative is 1/2 x plus 3/4 times x squared, our same exponent plus 1 divided by the exponent plus 1, minus the constant 4/5 times the variable to its exponent plus 1 divided by that exponent plus 1, plus our constant c. We can simplify this out a little to get 1/2 x plus 3x cubed divided by 12 minus 4x to the 4th divided by 4 times 5 is 20 plus c. Simplifying further gives us 1/2 x plus 1/4 x cubed minus 1/5 x to the 4th plus c. In checking our work, we find that when f of x equals 1/2 x plus 1/4 x cubed minus 1/5 x to the 4th plus c, the derivative, or f of x, is 1/2 plus 1/4 times 3x minus 1/5 times 4x cubed. The constant is removed because the derivative of a constant is 0. Therefore, f of x is 1/2 plus 3/4 x. Excuse me, there was a squared here. 3/4 x squared minus 4/5 x cubed. We can conclude the antiderivative here is valid because the derivative of that antiderivative is the original function. Example 3. Here we have two binomials multiplied together. As such, we will first rewrite the function as the product of these two. So we get 2x squared plus 2x minus x minus 1, giving us 2x squared plus x minus 1. Anti-deriving to get big F of x, we get 2 times 1/3 x cubed plus 1/2 x squared minus x plus c. To get these two bits here, we added 1 to the existing exponent. So 2 became 3 and 1 became 2. And in the denominator, which we wrote as a fractional constant, we added the existing exponent value to the understood 1 in the denominator. So because both of these had a denominator of 1, 2 plus 1 becomes a 3 in the denominator. So 1/3 x squared can also be written as x cubed divided by 3. And the denominator of 1 here plus the exponent of 1 here yields us 1/2 x squared, or x squared divided by 2. Again, we can check f of x equals 2/3 x cubed plus 1/2 x squared minus x plus c. We'll check to see if this is valid. So we know that the derivative of our antiderivative is the original function. So f of x is equal to 3 times 2/3, giving us 2x to the 3 minus 1 is 2, plus 2 times 1/2 is simply 1, x to the 2 minus 1 is simply 1, which we can ignore because that's understood, minus, we have a 1 exponent here, times our 1 invisible coefficient here, so this just becomes 1x to the 1 minus 1, which is 0, and x to the 0 is 1. 1 times 1, still 1, plus our constant, but the derivative of constant is 0. Thus, f of x equals 2x squared plus x minus 1. This is equal to our simplified version of the function, and because of this, we can conclude that our antiderivative here is valid.